Okay, great. Okay, everyone, so welcome to week 4 of our quantum mechanics exploration. It was nice to see some of you last night at the problem-solving session. I did not get a chance to sit in on a lot of it, but I think, from my understanding, Gabe really went through the whole calculation. So that's good, that's fine and dandy, but I told him not to do that next time, because I want to see if you guys can do it yourself. And I just want to stress one thing quickly before we get into today's topic. I don't really care if you get everything right on the problem set, or get every factor of 2 pi right, or get every sign. That's not very important to me, because I think I've said this before in a smaller forum. I really think anyone can learn how to compute things. I'm much more interested to see where your minds are at thinking about the physics. So don't stress out too much about them, but do try the problems, because you really can't learn without doing problems. It's very, very easy to trick yourself into thinking that you understand something by reading or by listening to someone talk about it. And then when you have to explain it yourself or solve a problem, you realize you didn't know as much as you thought you did. And then on top of that, in research, there is no answer to the problem. So you really have to rely on your creativity and intuition to make some progress. So I just wanted to mention that, just because I don't want people to feel intimidated by the problems. They're not meant to keep you busy for 20 hours. They're meant to make you think for 3 or 4 hours, and then you move on to the rest of your stuff throughout the week. They're not sort of meant to be these long, trust me, I could have made it a lot harder, but I don't think that really serves any purpose for either of us to have you stuck on these long computations. And if you guys end up studying physics in college, you'll end up doing all of that anyway. You'll end up spending 8 hours on a problem set and doing very long you'll do all of it. So that's not my purpose here, because you'll get that in university. My purpose is to see how you think about physics, especially considering that most of you haven't taken a lot of physics. So I really just want to see your intuition. So please don't feel like you need to do every calculation right. And if you don't do every calculation right, you can't send me something. Just send me whatever. Even if you didn't even do any math, just send me your thoughts about the problem, what you were thinking about, how you would approach the problem. You know, that's what I want to see. Of course, the first problem on these problem sets is always just to verify. So that's just a computation explicitly. But other than that, they're meant to make you think a little bit. And this new problem set, which will be up today, is no different. I'll put solutions up to the second problem set. Gabe writes up the solutions. They'll be up after 5 o'clock. Someone pointed out to me that I made a mistake on the problem set, which makes sense, because I kind of don't remember a lot of the stuff. So one of the, I think it was this, it was XY dagger equals X dagger, Y dagger. They should be flipped around. Okay, so if you work through it, so this should be Y dagger, X dagger. So if you work through it and you think you got it, that's okay. That means you have to go back and check it, because I wrote it down wrong. I should have looked it up on Wikipedia before I put it in the problem set, but I should have verified it myself. So that was the only mistake. Okay, any questions about logistics, the problem set, or anything? Quick questions before we start today? Just wanted to take a minute today. Otherwise, we can get going. Okay, great. And I think we have a lot of time until the first research paper was supposed to be due. So as that gets closer too, feel free to chip in or stop by tomorrow morning. As usual, I'll have my open question session from 9 to 10. Okay, great. So let's begin. So what have we done so far? Let's have a recap of the first 2 lectures. So we sort of started developing a measurement algebra. And we're using this measurement algebra as a way to describe some pretty odd physical phenomena, right? The character of physical law in the quantum realm seems to be very odd. it seems to be very predicated on probabilities, uncertainties. And so we have to see where this leads us next, because we aren't fully done reconciling all the weirdness of quantum mechanics. So today I'm going to introduce to you another very important aspect of the quantum mechanical program, as I like to call it, and that is the aspect of unitarity. So as you guys have seen in your homework, you derived the Pauli matrices using an SU2 representation, and the SU2 group was a group of, could be n by n in an SUN group, but you worked with SU2, so you worked with a group of 2 by 2 unitary matrices with determinant 1. And when you did that problem, you saw some of the characteristics of unitarity, namely that U dagger equals U inverse, right? And so these characteristics of unitarity will come back as we discuss unitary operators today. Another very interesting thing is that the unitary operator is used in quantum mechanics to take us from one orthonormal set of basis vectors to another set of orthonormal basis vectors. That's one of the main ways in which we use a unitary operator. A unitary operator is also used to take us from one eigenvalue of an observable to another. And you'll see what I mean by that in a little bit. It's also the case that unitarity becomes a very important tool in deriving and analyzing what we call the Heisenberg picture of quantum mechanics, in which to describe any state in physics, you want to talk about how it evolves with time, right? That's really the key. You want to tell me how a system moves and the dynamics evolve through time. And the Heisenberg picture creates a set of unitary operators such that the operators evolve with time and therein evolve the system. And in the homework, problem set 3, you will derive an equation of motion from the Heisenberg unitary operators, okay? And you'll explore that, and you'll see how these unitary operators, when used effectively, can take you from different sets of basis vectors and can also predicate the dynamics. Now, one thing I will say, when I say set of basis vectors, I really mean a complete set of basis vectors. I think I've mentioned completeness before, but completeness means an infinite set of basis vectors. That's kind of an important point. It's subtle, right? Because intuitively, you might say, okay, if you're giving me values of energy, there must be a finite number of energy states I can have. There must be a finite number of energy eigenstates I can occupy. Turns out you can have an infinite amount of energy eigenstates, all separated by discrete quantities. And I think Gabe had mentioned this to you because we were discussing after. He talked to you about why we even call it quantum. What do we mean when we say quantize? It's a fancy word, but all that means is that now the quantities that you have known and loved, energy, momentum, now come in discrete chunks, right? They come in discrete chunks separated by some multiplicative constant. In our case, that will be h bar. That's why h bar is so important, right? H bar is the smallest length scale we can probe, the Planck length, reduced Planck length. And each and every eigenvalue that comes from the corresponding eigenstates is separated by that constant, right? So it goes 1 h bar, 2, my values of momentum, for example, could go 1 h bar, 2 h bar, 3 h bar, 4 h bar, and so on. And that's all we mean by quantized, right? There is no 1.5 h bar as a value of momentum. And this will all make sense in a few lectures. The next lecture, we're going to talk about continuous quantum mechanics. We're going to start talking about wave mechanics, Schrödinger equation, taking our discrete states and talking about them and thinking about them as wave functions. After that, we'll do angular momentum, which in quantum mechanics is a very important dynamical quantity that we need to explore. We'll talk about singlets, multiplets, doublets, and so on. Group theory will also be essential in our discussion of angular momentum, but you'll get a primer on that in the next problem set. And then after that, we'll go to some quantum mechanical systems, namely the harmonic oscillator, and maybe a few other examples, I'm not sure. Then we'll spend a class and rederive all of the classical equations of motion from quantum mechanics using the WKB approximation. And then we'll conclude with the path integral, which will take us nicely into field theory. So I'm just taking a minute to tell you all this now because I sat down and actually thought about where we want to go. So in case some of you want to look in Townsend or look in Sakurai or look in Gottfried and Yang, now's your chance to do so. Okay, any quick questions before I begin on the program? Okay. Oh, see that you guys are typing in the chat, but I'm not looking at it, so. Okay, someone wrote, can you hear me? Okay, good, you can hear me. That was confirmed. I thought someone had a question. Okay, so let's begin. So let's just start off with the definition of a unitary operator. What do I mean? It's some operator, UAP, defined in the following way. And similarly, if I write it in the other way, I just get the same thing backwards. So it has two indexes, right? BA or AB, and it's defined in the following way. Okay, and we're going to play around with the consequences of such an operator. It follows from this definition that UAB dagger, the Hermitian conjugate, equals UBA, and similarly UBA dagger equals UAB. And you can confirm that in your own time. So let's work this out. Let's write out an expression. If I have the following, UAB and UBA, and one thing to note as we go through this, I'm going to be very, very careless with my indices. And you should be able to reconcile that with yourself. If you can, stop me, okay? Because these indices are like dummy variables. I can do I have a lot of freedom with how I label my K's and my L's and my M's and my Q's. So just think about that as we continue. Okay, so just start scribbling down something for that. So I'll write down something. So I'm using two indices, again, just to make things clearer, but obviously you could do this really any way you want. Again, it's perfectly okay to change the L's to K's here. Oh, sorry, wrote this bad. Right, and so we recover our identity relation, right? I won't use that, I'll just write it like this. Right, and of course, this equals 1. So you're starting to notice how these unitary operators work, and it's the same way we've been writing expressions before. You're just going to notice that now we have two separate indices, and these are going to help us go from one basis to another, right? Just consider these B's and A's to be different measurement symbols. This could be for position, this could be for velocity or something like that. Can I erase or? Okay. And please stop me if you have questions, as always. Or if you have a comment too. It doesn't have to be a straight question. So let's just write that the other way. Right, just to get some practice. So I can play the same game. Okay, and it follows from this that we can get the following properties. That UAB dagger equals UBA equals UAB inverse. Similarly, UBA dagger equals UAB equals UBA inverse. Right, and this is the unitarity property which you confirmed in problem set 2 when you were working with SU2. So now, what's the whole point of using a unitary operator in the most general sense? Like, why did I go? I mean, it seems kind of trivial. All I've done is really just added a separate index to play around with. But you'll see that this has profound consequences. So let's look at this now. If I have this cat, and I have the following unitary operator, and you work out these expressions explicitly. I mean, I'm not going to do that here. You should verify this. I'll get this. It takes me to the other basis. Similarly, I have this relationship. Okay, and we can play the same game the other way. Okay, so I'm going from one orthonormal basis to another. And also it follows that U dagger gives me back the identity element, and U dagger U also gives me back the identity element. Okay, so this is why these are so important. It's taking me from one orthonormal basis set of vectors to another. Yeah, is that good? Everything is clear so far?
When you do the manipulation with the indices at the top, are you like assuming that K is always equal to L, or?
Yes, exactly.
Okay.
Very good, very good. So yes, A and B are different dynamical measurements, but K and L are the same number. Does that make sense? So A and B could be positions and velocities, but they could both have the value of 1 or 2 or whatever. Does that make sense? That's subtle, but that's, yeah, good you pointed that out. And of course it has to be like that, or this whole thing would be a mess. Right? Because then this Kronecker delta would be 0. Or right, or even a Kronecker delta here with A's and B's would be 0, right? So you have to make sure you understand that point. So very good, yeah. Anything else before we continue? Okay. And again, we're working with discrete quantities here. So we're just building off of what we've been doing. There's no complicated integrals or anything. That will be next time. Today is sort of the last day of working with discrete quantities. And building up our toolkit, which is pretty important. Okay, so it follows from that I can write something like this in the following way, using my unitary operators. And again, as Kelly pointed out, the distinction between K's and L's and A's and B's is pretty important here. And again, you should work out this expression, like fully work it out, right? You know the definitions of these things. Make sure I didn't make any algebra error. Okay, now let's talk about a quantity we're very familiar with. And let's sort of recast it into a different light, into a more linear algebra light. Okay, so let's look at the expectation value, which is something we know and love. And we've constructed it in this way. And we've discussed why we've done all of that many, many times in depth. We've worked with these objects. And we know now that when we act on a state vector, a state ket, my in-state, I get back my in-state with some number. Similarly, if we do it on an out-state, I get back the same result. I get back some number. So now I'm going to just define these for you in the more linear algebra speak. So this number is called an eigenvalue. And when you use matrices, you should look up, if you haven't yet, how to find eigenvalues and eigenvectors. It's not very complicated. And it's literally the linear algebra definition. It's not anything different. So, and it's pretty insane how this actually works out like that in the whole matrix program. So these are the eigenvalues. And these vectors, these state vectors, are eigenvectors. So now you know why I keep referencing these. And it turns out that any observable will form a complete set of eigenvectors and eigenvalues, corresponding eigenvalues. Any observable that's Hermitian will form a complete set of these objects. You could have a complete set of position eigenstates and eigenvalues, momentum eigenstates and eigenvalues, energy eigenstates and eigenvalues, so on and so forth. Does this make sense? And you should be, I mean, it's nothing we haven't seen before. It's just sort of developing it further into the more, developing it further with respect to the linear algebra side of things. Okay, so let's look at another example of how we can play around with the expectation value with unitarity. Okay, so let's say I define my expectation value in the following way, which is our canonical form, standard form. Then I can insert a unitary sorry, my bag keeps small. Let's make sure. So, yeah. Then I can insert a unitary operator and recover one basis from another. Hold on, let me work this out in my head. Oh yeah. You're going to need one more unitary operator here. And so basically, I can recover one expectation value from another with the following expression. Okay? So these unitary operators are useful, very, very useful. Because if I can define a unitary operator in my basis, I can recover any other basis from it. Does that make sense? Is there anything confusing about the significance of that? Okay, good. And more generally, I can write this combination. Sometimes I get a little, I need to stop and think about where my B's and A's go. Yeah, I can write this combination as this. Okay, so that was the basics of unitarity. Now we're going to go into something very, very strange. I warn you, I have not found someone derive this, what I'm about to show you in this way. So it's very not rigorous because I'm not a mathematician. So my friend Johnson here will be very, very dismayed. So let's have a dialogue if something's not clear about what I'm about to show you. But does anyone have any questions about unitarity in the most general sense and the mathematical conditions of it? Okay, great. Also to note, when I say U dagger equals U inverse, I also mean that for a unitary matrix, right? We should start thinking in terms of matrices. That's pretty important. You did that on the homework. That's why I didn't stress it, but I'll just say it again for those of you that didn't get a chance to work through problem 3. Okay, so I'm going to lay down the scene now of what we're about to derive. Let's go back to our commutation relations. So we have some commutation relation. We know it equals this. Can someone, oh my God, can someone tell me, and I know you guys know this because Gabe told me explicitly, he discussed this with you. Can someone tell me what the physical meaning, and also let's consider A and B to be 2 dynamical variables of interest. So can someone tell me what the physical meaning is when I say the commutator between A and B vanishes, i.e. it equals 0? Can someone tell me what that would mean physically? What can we say about the 2 observables if their commutator vanishes versus if it doesn't vanish? Just shout out.
So they are just equal, right?
Sorry?
They are just equal?
Well, that's true. That's true. But I'm trying that's true in the mathematical sense. But physically, what can we say about the dynamical quantities?
The order you take them in doesn't matter?
That's true too, mathematically. But if I have, like, let's say A and B are like energy and acceleration, and I say that they don't commute, meaning when I take their commutator, I get some non-zero number. Physically, what that tells us is that the 2 measurable quantities are not complementary, in the sense that you can't measure both of them mutually to a high degree of certainty. In other words, if energy and acceleration do not commute, I can't measure energy and acceleration perfectly in my system. That's very important. I mean, this commutator has a real meaning. It's not like we just define this math and say, oh, every dynamical variable must maintain some commutation relation just because we want it to be like that. No, there's a real reason we say that dynamical variables, which will be promoted to operators, which you derived an operator in the homework, must be promoted to commutation relations. There's a reason, because it tells us something about the physical system. Okay, and so now let's do a deep dive into this, and let's see if we can derive some commutation relation using our knowledge of unitarity. Namely, we want to derive a commutation relation for the 2 most important things in any system, position and velocity. Okay, we want to see if our positions and velocities are both complementary to one another, because in any classical system, what are our kinematic equations all comprised of? Positions and velocities, right? So that's what we want to explore. And we're going to call our velocities momentums, just add a mass. But for all terms and purposes, momentums and velocities can be treated equally. And masses are not so important for now, but I'm going to call it momentum. Okay? So we're going to start very abstractly, and then we're going to see if we can figure out something about the commutator between those two objects. Okay? In a discrete sense. We haven't talked about wave functions. We haven't talked about any of that. We're just using our conditions of unitarity. Okay? Also note, we know nothing about the physical dynamics in quantum mechanics of momentum and velocity, right? We don't have an analog of velocity and position from our classical knowledge to quantum mechanics, right? If I asked you guys who have taken physics 1, what would be the velocity in quantum mechanics? You'd be like, well, I don't really even know. So just remember that, because some of the labeling can be arbitrary. And if it works out to match the physical description, then we can keep it, which we'll see. So let's begin. Let's consider a unitary operator that does the following. Let's consider a unitary operator that, when acted upon the basis vector, takes me to the next eigenvalue. Okay, and you can construct a unitary operator that does this. Therefore, if I have this unitary operator acting on the same basis, I get the following. Okay, so I can do this. I can go from one eigenvalue to the next and use my unitary operator to make that cyclic movement. We also have this condition that u to the n power must always equal 1, right? You can have any combination of unitary operators, and when you multiply them together, you get back 1. You could have u dagger equals 1, u dagger u equals 1, u dagger u equals 1, so on and so forth. You can keep constructing sets of unitary operators and they will all equal 1. It doesn't even matter how you put them together. So now I want to try to find a value, u prime, such that this relationship holds. This should be an exponent. So what can I call a u prime, right? And this is similar to what we did with the phase, right? Remember, we put some operators in between our state vectors, right? We had some a prime, m of b, a prime. And then I said, oh, but you could also literally put, right? We had this, I'll write it out so it's explicit. And I said, oh, you could have this. Similarly, we have a unitary operator, but I could also easily just put a phase, right? And all that would mean, all that would do is shift these state vectors around. So similarly, I wanted to find a number, like a value, an exponential value for my unitary operator that leaves this relationship intact. Again, please stop me if anything doesn't make sense. I'm going to go slow. Okay. So it's similarly to what we did with the phase. So here's how I want to define my u prime. Where k and n are integer values. And note that when k equals n, what do you get here for this exponential? E to the 2 pi I is equal to what? 1, exactly. And so this will maintain my unitarity relationship, right? Because I can have any two integers. If they're equal to one another, if I set up my unitary operator in that fashion, this relationship holds. Does that make sense why I chose this value? And obviously it's motivated by some physical intuition, right? Because these are plane waves, right, in a complex plane. And so I want to see if I can extract some physics out of this. Yes, no? Okay, it's abstract. We're not going to see the physical meaning for a little bit, so just hold on. Okay, so let's derive some relationships. So I have this, un minus 1 equals 0. And I can rewrite this in the following fashion. Where UK is none other than this new phase-like quantity we've constructed. And note that in my multiplicative series, I have the condition that k and n are the same. They're just integer values from k to n. And now I'm going to do some algebra. I'm going to factor something out. And the algebra might not be so clear. I had to spend some time working on it, but do confirm this on your own, that you get the following result. Okay, you can always do something like that. I'll explain this in a minute. Okay, so what am I doing here? And if the algebra isn't clear, you might have to work through it or come tomorrow, because it took me a while to work through this algebra. But you'll see that all of these quantities are equivalent. I just wrote things in different ways, right? You're always going to get some zero. And all I've done, the reason I've done this, why am I doing this mathematically? There's no physical reason to it. It's because I've introduced a new unitary operator in another basis out here with values of L. Okay, that's the only reason I wanted to do it. So now I have two unitary operators I can play with. The L's and the K's. That's all. That's the only reason I've done it. And you could even skip all these steps and just say, okay, I want another unitary operator with K's. But I thought I'd just show you how I get that from this initial description. Any questions? And so you can see here now, I have another definition for unitary operators. Okay, I can define this object alone as a unitary operator. Okay, and we're going to play around with this for a second. But now I have two things to work with, L's and K's, which is good because I want to find out if I can figure out a commutator for two different dynamical variables, right? So somewhere down the line, I had to introduce another unitary operator that defined my other set of basis vectors. Yes? No? Maybe so? I see blank stares, so. Oh, I think my camera. Yeah, I'm back. Sometimes it just, okay, good. So let's play around with this object now. By the way, I don't know if I'll show you the algebraic identity I used to get that last relationship in case you want to do it at home. I mean, I have it down, so I don't even remember it, so I need to look. Yeah. Okay, that should be a familiar identity. Okay, and now I've defined some new operator. Don't worry about this for now. For those of you that have read Townsend, this is a normalization, which we'll talk about in a second. Right, for my algebra, now I have a new definition for a unitary operator, where my UK is some function of E, or some kind of exponential. You can note that this operator is Hermitian, okay? And so let's just write down an expression with it, which for the sake of time, you can work out at home, but all this would be a 1 over n. Right, I'll put the, oh shoot, this should be a over. Okay. Does someone want to tell me where this 1 over n comes from, for those of you that have been reading Townsend? Okay, that's okay. All this is normalization. You can check this for yourself. What do I mean by normalization? Check that if you didn't have this, this quantity would not equal 1. We just need to add that there to make sure this thing equals 1. Okay, when you play around with the n's and the k's and the l's and so on. Okay? And, you know, it turns out that if you have this following thing, it could be any arbitrary thing. You get this. Therefore, the normalization of a normal inner product is just this. And that's why you keep seeing 1 over root 2's everywhere, because this is where it comes from. Yeah, does that make sense? Are we really confused? It's just playing around with some math. It's not really doing anything fancy right now. Let's play around with this a bit more. Okay, so if I have this, I can now write it in the following fashion. Right? Because this is my unitary operator acting on this to give me the other basis state. Similarly, if I have this, right, I just get it in reverse. So hopefully this clears things up a little bit. Even if all of the algebraic steps were not so clear. Yes? Okay, so now the whole point of this was to introduce another unitary operator in another basis. And so let me explicitly define them. How do I want to do this? Let me think for a second. If I want to introduce two new operators, yeah, that's right. I want to make this an L, just to use what we've been using. Okay, there we go. So now I have two things to play with. Okay? And all of that algebra was just to get this and get these forms, which are going to be crucial to define our commutator. Any questions? No? Everything's good? Okay.
Wait, okay, I am somewhat confused about, I see, like, you know, the use of K, that's like a new unitary operator in a different basis, like, because you use L this time. But, and then the thing you did with like the U is just what you said before, right? With like raising it to this next, wait, I don't know. Because I don't, what you did with like the U and then the cat V sub L, that's like just raising it to the next eigenvalue?
Yes.
Okay. And then in the next one, like since the V is inside the cat, I don't know what it like.
Right. Good.
Out and multiply it.
So you're saying, what you're saying, which is a good observation, is that this should be a V, right? Based on what I've been sort of spelling out. That I would need the unitary operator in the same basis to take me to the next eigenvalue. That's a fine point. So let me think how I should articulate this in a way that's not confusing. Yeah. So what you said is true, but again, what you need to remember is there's two things that are sort of important here. First off, we can do it that way. That's the first thing I'll say. You can literally just keep this V here and put the U there and, you know, switch them out. And if you want to keep all the labels straight and everything. But I just want to make it clear that I'm not being dogmatic. You could easily do it the other way, just by redefining what your unitary operators are. The U's and the V's are not necessarily defining any, they're not defining any basis, and they're not defining any physical quantity. Does that make sense? And so, like, in some sense, they're equivalent. They're the same thing, U and V, right? My unitary operator is really the same thing. So if U can take one eigenvalue to the next eigenvalue, V can do the same thing. And I guess to not be confusing, I could just do this. I mean, it doesn't make a difference, right? My point is I wanted to write them flip-flop to just stress to you, don't mistake your U's and V's for operators in the physical sense. They're not physical. Does that make sense for my rationale there?
Yeah, I think so.
Okay. In other words, U and V are really, I don't want to write in equals, They're the same thing. The reason I'm labeling them differently is because I'm defining them to do different things.
And okay, I get that. Can you, when you write an operator, can you put like the little hat on it just so it's a little bit clearer?
Okay. Okay. There.
Okay, cool. Thank you.
I will forget to do that though, so. Okay. Okay, and they all maintain the same properties as before. Right, Kelly? So now you're starting to see they're kind of the same thing. It's just so like I don't have like 5,000 U's here. And then you get confused, like what's even going on, right? Because we're working with two different bases, right? We're working with V's and we're working with U's. Those eigenvalues are different bases, but U and V are kind of the same unitary operator. Does that make sense? Okay. I didn't want to have like 50 U's out. That's really the only reason. I'll say one thing though that's important. Why did we go through all that math to get another basis L or VL? Does that make sense? Little VL or little VK. Okay. Okay, now I just have a bunch of, okay, literally I just scribble down all these identities on this sheet of paper. So if they're wrong, come and correct me because I did this late at night, but I'm pretty sure they're right and it will get us what we want. So those of you that want to help on this textbook, this will be your job to correct all my notes when they're done because I'm very behind on them. So I'll just scribble down all the identities I got. Show you some relationships between this V and U now. Okay. And these final three will be crucial. So we'll name this one alpha, we'll name this one beta, and we'll name this one rho. Okay. These three identities will be what we use. And theoretically, all we're doing is playing around with unitarity. We're not really doing anything complicated here. I mean, it shouldn't seem too, if it seems complicated, just sit with it for a few minutes. You'll be fine. Because it's really just moving things around, moving signs, manipulating things. It's not very complicated. Any questions before we put this all into a nice form where we can work with? Johnson, is the rigor on point, or? Mathematicians, gotta love them. I shouldn't block the board.
Sorry, the denominator of the 2 pi I is, oh, sorry, in like at the bottom. Yeah.
What about it?
What is that? Sorry.
It's minus 2 pi I over v k
Yeah.
f.
Sorry.
No, sorry. No, that's fine. My handwriting is. I'm trying to write big. For those of you that stick around for QFT, my handwriting will be smaller, and this whole board will be filled because the commutations are very, very long. So I hope it doesn't become too difficult. We'll have to see. Okay, can I continue, or? So I'm going to set up the problem, and then we're going to take a 5-minute break. Okay? So let me set up the problem. Let me set up what I want to do. Okay. So I'm going to do the following. I'm going to set some constants equal, so 2 pi. Do I want the I? Yeah. No, I don't want the I. The I can't do that with the I. Equal to epsilon squared. So some really small number. The squared is to make some people happy. Don't really need it. Okay, and then I'm going to do the following, which might seem scandalous. But again, since you have no intuition of quantum mechanical observables, we might as well do this and see what happens. That means that U is going to go to some e to the I epsilon, and I'm going to take my dynamical quantity and call it Q, position. V, I'm going to play the same game, except I'm going to call it a momentum. P. Right, with this. Just as a notation thing. Okay? So I've set up the problem. Come back at 10:35. You have 3 minutes. Get a drink. And then we will have a marathon with our first long computation. So. Do you guys who are in here, do you feel like the problem sets are at the right level, or are they taking you way too long?
I think they're fine. Like,
Okay.
Yeah.
Okay, good. Okay.
So, and I just have a question regarding this. So, I didn't have a chance to attend the problem session, so I've sent a photo. So, could you look at this, please? So problems.
Yeah, can we do that? I can stick around for a bit after, so we can talk about it after.
So did you just, like, it's a quick one. Did you just lose that dx in that second?
Yeah.
Okay. Okay, thank you. That's all.
Oh man, my typos are gonna become legendary. For those of you that have used LaTeX, you know it's very, very easy to make typos. It's just really, it's inevitable. Okay, let's crank this thing out. So I'm going to use these identities and write things in the form, in exponential form, using the way I've defined things. So let's begin with beta. We're not going to need alpha. So I might as well have, I'll just get these off now because that was a little unnecessary, but it's fine. Okay, so v to the minus L is just v to the minus I epsilon P L. Then we have a UK, and now you just follow along with me. This should be an E, not a V. UK is just E to the I epsilon KQ. Then we have another VL, E to the I epsilon PL equals E to the minus 2 pi I. Oh no, this is an epsilon now. E to the minus K epsilon L epsilon UK E to the I E epsilon Q K. I'm missing an I. Yeah. And now I'll write the bottom one. E to the I epsilon QK, E to the I epsilon LP, E to the minus I epsilon AQ equals E to the minus I K epsilon L epsilon, E to the I epsilon PL. Okay, and now we'll call these alpha and beta, because now I'm going to work on them separately. So let's work with alpha. So I can rewrite this thing. So I'm not going to write out, well, I can. E to the minus I epsilon PL, E to the I L equals E to the minus I K epsilon. Q, oh, I want the minus on, so Q minus L epsilon. Yeah. And I'll do the same for beta. I'm just rewriting. Minus Thanks. I cubed epsilon minus, there's no q. K, L, P, L. Am I looking at the wrong thing? Let me just make sure I did this right. There's no P here. There's an epsilon. Yeah, minus. Yeah, so this L will get factored here. Just I, L, epsilon, P minus K epsilon. There. Algebra was a little slow. I'll make this a little more clear. It's kind of messy. Yeah? Just filling in and taking out some stuff and putting in some stuff. So I'll leave our alpha and betas up. Give you a second to write it all down. And so now I'm just going to expand some of my exponents. And I'm going to make the following substitution. I will have L epsilon go to some Q prime. And I'll have K epsilon go to some L prime. What am I? Some P prime. Why can I do that? It's just moving to some other eigenvalue, right? Which is how we've defined these things. And I'm putting them in the same basis now. That's all. I can easily make that switch, right? So now what this expression, what alpha is telling me is I'm going from some position eigenvalue to another in exponential form. And what beta is telling me is that I'm going from some momentum eigenvalue to another momentum eigenvalue in exponential form. And so let's expand these exponents. So alpha becomes the following. Let me stare at it for a second. One minus I Q prime. Plus some higher order terms times Q, 1 plus I Q prime. Just expanding the exponential. And I can do the same with beta. Should be the same, so I'm not even going to really think about it. This is good stuff flipped around. You can ignore higher order terms, doesn't matter. You're not going to contribute because of the epsilons. Okay? We'll do a little bit more algebra. Alpha goes to Q plus I. Let me make sure. Yeah. PQ. QP minus PQ plus higher order terms. I'm just going to write this order epsilon. And if this is to order epsilon, then the higher order terms drop out. And of course, this equals my position eigenvalue, number 1, to position eigenvalue 2. Or this is a minus, so it's really vice versa. Just the difference between the two. And similarly here, I get the following. This is just expanding the exponential, doing some quick algebra. It's not really so dramatic. And you should see something kind of crazy pop up. I don't know if any of you see it. Shout out if you see it. Which when I got this, doing it this way, I was very happy because I like to think Heisenberg did it this way, okay? You heard it from me. I'm sure his derivation of this is somewhere. Okay, what do we see, guys? And just to make things look pretty, I'll get rid of these and I'll rewrite this up here while you stare at it. Anyone want to shout it out?
So this implies that the commutator of position and momentum is non-zero?
Exactly, very good. So we figured out that the commutator between Q and B, P cannot be 0. Moreover, we figured out that the commutator between Q and P is I. And in canonical form, the commutator between Q and B would be IH bar. I've just not, brought in this unit because we always set H bar equal to 1 in quantum mechanics. And moreover, as you'll see, these Q's and P's will become operators. Pretty cool. So playing around with unitarity, and obviously I want to stress, we have sort of defined Q and P. We could have made Q and P random letters, but you'll see that this represents the dynamics of positions and momentums. And you should get a feel for that already because of the way plane waves are written out. They're written out as some e to the I, P, X, right? For those of you that have seen plane waves in physics. This is intuitively what we're working with. It's not like I've randomly just said, K is equal to P and L is equal to Q and whatever. I have some inkling of where I want to go with this because of the way plane wave solutions are written out. Moreover, it's even more scandalous if you write it like this. Right? You can even write it in this form. Plane wave solution. Just shift it. So this is following straight through from the classical analog. It's not really, or not classical, because we have this I. So I speak to this in strictly a mathematics sense. Okay, so now I want to do the same thing, but in a different way, okay? Does this all make sense how we got? It's okay if the details aren't so clear. You can sit with it and you'll figure it out. But the significance of this is crazy. And what does this tell us physically, folks? This tells us that even though classically I can have a kinematic formula with both position and momentum clearly defined, in quantum mechanics I can't. I cannot tell the position and momentum. I cannot tell the position and momentum of a system with absolute certainty at the same time, which is kind of insane. It's another weirdness of quantum mechanics. And so we see that in quantum mechanics, we don't have systems where we have full information on what's going on. We kind of are dealing with probabilities, and then on top of that, our dynamical variables don't commute. Which is why in quantum mechanics, the commutation relations are so important. Because in classical physics, all the commutators vanish. Right? I mean, there's no real need for them. Right? And classically, you'll deal with things with this, Poisson brackets. You will define some relationships, but they're not going to be as important as these. Any questions on the physical significance of the commutator? Okay. So I want to show you one more thing, which is neat. I want to show you how we can get Schrödinger's differential form from this same approach. And what we're going to do is we're going to derive the momentum operator, which you did in your problem set, which you derived as h bar over I ddx. Or in your problem set, we called this g hat for Glenn. I didn't want to give away that you were actually working with momentums. And remember, this I was missing in the P set. And you got a complex value. I shouldn't even be saying this because it's not 5 o'clock yet, but it's okay, I gave it away. You'll get a complex value for your observable when you work out that nasty integral. Okay. So let's see if this makes sense. So let's work with some. Do I want to do it this way or the other way? Let me see. Yeah. Well, I can write these following relations now. Yeah, that's true. Whatever. Let's just work with something like this. Okay. The minus sign is up in the air. it's scandalous. You're going to have to think about whether you need it. So let's just consider some arbitrary end state. And I get the following. Doesn't matter what that end state is. Okay, let's play the same game. Let's expand our exponential. Higher order terms. Just expanding the exponential. And so I can recover this same object in differential form. Let me just make sure I'm thinking through this. Yeah, I don't want that. Yeah. Yeah. Right? Because this is just really the derivative of that exponential. Make sense? Using the chain rule? Are we familiar with the chain rule? It's okay if you need me to go over it. Are we sure we're familiar with it? Okay. If you're not, come tomorrow. I'll show you. I don't mind. Okay. So let's write this in a very, very weird form. In a very suggestive form. Arbitrary end state. And just using this relationship, we can unplug, pull out. That'd be a 1. Let me look at this for a second. Yeah. Oh, good. Yeah, because this is being pulled out. And you get your p hat. So if we treat this expansion as a derivative, we can play some algebraic games, and that's what Schrödinger did, because Heisenberg came up with the unitary time development operator representation first, which you'll see in your homework. And then Schrödinger came up with this differential operator form. Okay, so there you go. We get p hat just by playing the same game. I hope I did that right. Let me check. Yeah, looks good to me. And for those of you that struggled through the homework, I hope this gives you some happiness to see it pop out at the end. To see this object pop out. And remember, the h bar, we have a very bad habit in particle physics. We just do this. This is my favorite thing ever to write, because I hate keeping track of C's and H bars. Okay, so let's recap. So we have derived both the Schrödinger differential operator method and the Heisenberg commutation relation simply by looking at unitarity. That's all we did. We looked at unitarity, we looked at a unitary operator, we played around with the characteristics of both. And we see that playing around with combinations of unitarity and playing around in this plane wave sort of space, right? We can derive some pretty profound results that would really, really contradict our intuition. So it's pretty amazing how such a simple concept of unitarity can really lend itself to this sort of thing. It's quite phenomenal. So next time we're going to start talking about continuous Q and P. And we're going to work with wave functions. And we're going to take all of our, and I'll tell you what a wave function is. I'll tell you why it's important, how we use it. The probability amplitudes in the discrete language really transition nicely into our continuous description, namely that you're going to start seeing objects like this, like you saw in your homework, where the state vectors are wave functions. Okay? Instead of discrete numbers, the state functions are continuous, and the probability amplitudes are defined over a continuous space. Okay? In other words, if you have a wave function that looks like this, in the complex plane, then and this is some position, your particle has this much probability that it's here, this much probability, it has more probability that it's at this position, and so on and so forth. Right? So that's what we're going to get to next time. And then we'll sort of transition away and talk about angular momentum. Okay, great. Any last questions before we sign off? Okay, great. And I encourage you to come tomorrow in the morning if you want to discuss your paper, if you want to discuss problem set 3, if you have any questions about what we talked about today, or if you have any questions about life or science in general. That's the place to come and chat. Those of you that have come, I think we have some nice conversations Sunday morning. So hope to see more of you there. Okay, great. I'll be on for a few minutes after if any of you have anything to discuss. And I'll see you guys either tomorrow or next Friday at Gabe's session or next Saturday at our next class. Thanks again, folks.
Oh, so Gabe's sessions are they all going to be moved to Fridays now?
I'm not sure. Email him.
Okay, all right.
I'm not sure what he wants to do. I haven't had a chance to talk with him about that. I think from my understanding, they work better for him for the rest of this term. I'm not sure how things will work in the spring. Because for you guys, fall and spring is the same.
Yeah.
For us, fall and spring are totally different beasts. It's like starting over again. So we might have to shuffle around days and things. So we'll have to see. But I'm not sure. Ask him. Again, if Friday nights don't work, set up an appointment with him for another day, for a half an hour or something. He'll meet. It doesn't have to strictly be Friday nights. So.
All right. Thank you.
Yeah, thank you. Have a good one.
Thank you.
Thanks. Take care.
Bye.
Bye-bye. See you guys.
Thank you.